What if a network of sensors could think as one, measuring the world with quantum-level precision that classical technology can't touch? That's exactly what scientists in Korea just achieved with something called multi-mode N00N states. It's a new way to link distant sensors using the strangest power in physics, quantum entanglement. Here's what that means. Imagine you're trying to synchronize two clocks, or detect a tiny vibration miles apart, or measure an average change in temperature across several distant labs. Normally, each sensor takes its own measurement, and you average them out later. But even if each sensor is perfect, there's a fundamental wall called the standard quantum limit. It defines how precise classical light and measurements can ever be. To get better, you need quantum entanglement. That's where multimode N00N states come in. In a traditional two-mode N00N state, all photons are either in one path or the other, a quantum superposition that lets you measure phases with extreme precision. Now imagine stretching that superposition across multiple paths or modes connected to different sensors. The photons are shared among them in such a way that you don't know which path they're in, but collectively, they act like one coherent team. In plain English, it's like giving every sensor a headset and connecting them through quantum Wi-Fi. When one node feels a change, the rest instantly reflect it through the shared entanglement. The network behaves as if it's one massive supersensor, even though each node is working locally with its own tiny beam splitter and photon counter. The Korean team built a simple but elegant experiment to prove this. They created a four-mode 2002 photonic state. That means two photons spread across two nodes, each with two optical paths. Each node added its own phase shift using wave plates, then measured the outgoing light with 50-50 beam splitters and superconducting photon detectors. Using clever math, specifically a maximum likelihood estimator, they combined the local results to find the average of the two phases. The outcome? They beat the standard quantum limit by 2.74 decibels, hitting the Heisenberg scaling that defines the ultimate bound of measurement precision. Now let's unpack that for people who don't live and breathe physics. Picture two friends on opposite sides of a city, both tossing coins, but somehow, every time one gets heads, the other gets tails. They're linked in a mysterious way that no classical connection can explain. That's kind of what happens with entangled photons in a multi-mode N00N state. Their behavior isn't random, it's correlated at the quantum level. When these linked photons pass through local sensors, the combined outcome reveals the global picture with much higher precision than regular light ever could. Why is this cool? Because it's not just a physics trick, it's a glimpse at how future sensor networks will work. Imagine telescopes spread across continents acting as one coherent eye, or fleets of satellites mapping gravitational changes with quantum precision. Think about navigation systems that sync time so accurately they could detect underground movement or dark matter interactions. Multi-mode N00N states bring that vision closer, and they do it using surprisingly simple, real-world components. The same kind of optics you might find in advanced fiber networks today. This breakthrough is more than a proof of concept. It shows that distributed quantum sensing can reach the highest precision nature allows, even when each sensor works independently. You don't need a giant central quantum computer, you just need the right kind of entanglement shared across the network. In the future, researchers plan to expand this approach to more nodes and more photons, using metasurface chips to generate complex multi-mode entanglement on demand. They're also exploring ways to make the system resistant to noise and loss, so these quantum networks can work outside the lab, on satellites, in cities, and even underwater. So next time you think of quantum technology as something locked away in a physics lab, remember this: entanglement isn't just for quantum computers. It's for sensing the world with impossible precision, and with multi-mode N00N states, that precision can now be distributed everywhere. Check out more at newsway.com.